Hello, my name is Daniel Schwartz, and I'm the author of Regularization and Sparsity for Adversarial Robustness and Stable Attribution. The other authors were Yeet Alparslan and Edward Kim. Now we all know that deep learning has drastically improved computer vision tasks. There has been work on image classification where you're attempting to classify what an image is. So in this first image here, we have a picture of a cat, and it's able to locate there is a cat there. There's even more specialization where we can localize where that cat is. So as you can see, there's a red box surrounding the cat in that second image. Another work similarly related to that, but done on multiple objects, is object detection. So here we have a picture of both a cat, a dog, and a duck, and able to locate those bounding boxes for where those cat, dog, and duck reside. Additionally, there's been work on image segmentation, which takes a step further than object detection, and this is actually tracing the borders and edges of those objects. So as you can see for the two cats, they're located in those red bounding boxes, and it's more than just a box, but a trace around their border. Similarly with the dog and the duck, there's also been ample work on facial recognition, detecting if I walk through a security camera, it's able to detect this as me, Daniel Schwartz, as opposed to anyone else. And this is greatly improved by deep learning and computer vision architectures. Some in particular are the following that I listed here, which we do our experimentation on. There's ResNet, which is a deep model with more layers and has these things of identity shortcuts. And what an identity shortcut is it's able to skip one or more layers by performing identity mappings. And the authors have shown that it is easier to optimize these residual mappings than to optimize the original unreferenced mapping. And overall, the intuition for this architecture is that these deep residual learning frameworks are able to use just few stacked layers fitting an underlying mapping, which can explicitly be fit by residual mapping, and it's easier to optimize than actually going through all the actual original mappings. Another architecture introduced by Google is called MobileNet, and this is a deep learning model which is actually tuned to work for mobile phones such as iPhone, Android, and so forth. And the way it's able to do this with limited resources is by using a depth-wise separable convolution. And as you can see on the image on the right, I'm trying to illustrate what that is. And on the top, figure A, it shows just a standard convolutional filter, which we're all probably familiar with. But what this actually focuses on is the depth dimension, which is the number of images, the number of channels in each image. And what a depth-wise separable convolution does is it splits a kernel, as you can see in A, into two separate kernels, B and C. What these two convolutions do, the first one, the depth-wise convolution, is it's given an input image and it convolutes over that without changing the depth. So for instance, each kernel iterates one channel over the image. Otherwise, the pointwise convolution, which is the second part, uses a one-by-one kernel, and this kernel iterates through every single point. And combining these two filters, the depth-wise convolutional and the pointwise convolution, it's able to do the same work as the standard convolution, but with less computation. And this is beneficial for running a deep learning model on a mobile device that has limited resources. And finally, we have the VGG16, which is a variant of AlexNet, and it uses these large kernels followed by many small 3x3 kernels, and it's able to do the same work. It's showed very promising results on many big data sets such as ImageNet. A common thing that these computer vision architectures fail at are these adversarial attacks, which we illustrate here on the bottom. And what that shows is an image such as like this panda here, and how the original input image added with some epsilon times some noise, and you can see it looks almost indistinguishable to the human eye of a different picture. But what this is actually classifying is originally it was 60% confident that it was a panda, and now after you add some noise, it's almost 99% confident that's a gibbon. And for those of you who don't know what a gibbon is, we have an image here on the right. And some specific attacks that are used to create these adversarial attacks. One is called deep fool, and what deep fool is, it's an untargeted white box attack that all its objective is to just misclassify an image, and it does this with as minimal amount of perturbation as possible. So for a binary classification problem, there's a hyperplane that separates the two classes, and what deep fool does is it takes an input x and projects it onto a hyperplane while pushing it just a little bit beyond to misclassify it. So it's untargeted, so it's not trying to push to a specific class just something that won't be the correct class. Another one is fast gradient sign method, and most image classification architectures are in fact deep neural networks, and they learn by updating weights via backpropagation algorithm, which then computes the gradients. And what fast gradient sign method does is it uses the gradients of those neural networks to generate an adversarial example by using the gradients of the loss with respect to the input image to create a new image which maximizes that loss. And then finally, we have projected gradient descent. And what this is this is a targeted white box attack, which actually uses fast gradient sign method, and it iteratively uses it to attempt to get to a different class that you're trying to aim to. So because this is targeted, if I want to call the panda a paper towel holder, I could then have that as my objective class and iteratively use the fast gradient sign method until I achieve that class that I'm looking forward to. Another common thing that is used in computer vision problems are attribution methods. And what that is saying is kind of determining what parts of an image are able to contribute to a classification. And there's two common techniques to do this. The first of which is the sliding patch method, which hides portions of the image and measures how much that classification outcome changes. And by doing so, it's able to create a heat attribution map of those changes that occur in the prediction. So this is almost just masking pieces of the image to see what actually contributes to the main classification that the model is trying to do. Another technique used is GradCam, and what this does is it uses the gradients of the output in the final convolutional layer. So most of these computer architectures are deep neural networks. So taking that final convolutional layer to localize those image segments, which greatly attribute to the classification as a whole. And this is computationally less expensive than the sliding patch method because it's not brute force every single frame block in the stride to see what is classifying. And we have here a test image to show the first row is trying to classify a cat. And you see the original input, there's nothing done to it. And then in figure C, you can see GradCam creating this heat map over the cat, where the rear of the cat is most important to the classification. And then in F, you see this applied to ResNet, where the head is the most important part. And this is what's actually classifying the image as a whole as a cat. So this isn't in itself object detection, but it's just showing you from what parts of the image are most important to the classification as a whole. Similarly, it does the same thing with the dog, where in the original image, it's just the cat and the dog, but in I, you see that the head is very important to the GradCam, and then using ResNet and GradCam, it shows that right here, the dog is classified based off the front and head of the dog. And these are just common techniques to see how well my neural network is doing and what exactly it's learning. Because many times people think of neural networks as a black box, what these attribution methods do is actually explore what is going on within the neural network. Two common principles that we use in the study are regularization and sparsity, and they come from biology, where regularization is often used in machine learning to reduce overfitting and increase robustness of the model, and sparsity is used to increase generalizability and pushes the coefficients to zero. And sparsity is a common thing in biological principles and the neuroengineering framework. And as you see here in this graph, we're able to explain that the average density of neurons in a CNN decreases as you increase the regularization. So we have a regularization of 1e to the -4th all the way to 1e to the -7, which is forcing the parameters in our system to go towards zero. And as the epochs increase, we get almost zero average density, which is how many of the neurons are active within our model to predict something. So a neural network works by changing the weights to say how much of this node is active. And you can see that the accuracy increases as we decrease the regularization. So here with a regularization of 1e to -5, we're getting almost zero average density, where in the accuracy it's almost 97.5%, which is similar to the base model without any regularization. So not only does it increase the accuracy, but it also decreases the amount of neurons to be active. Another example experiment we ran was the robustness against adversarial attacks with this attribution method. So clear here, we have an attribution heat map generated by the sliding patch method, where the first row shows the original image and then the heat map generated for the resulting class. And we're using a patch size of 4 and we jump size of 2. So as we increase the regularization, we get a more clear picture, it seems like, of what is actually attributing to the classification. So in the base, without any regularization, it's just a small blob of the boat. But as we increase the regularization, it looks like it's getting more and more of the boat. So it's able to generalize in the future and be more specific about what specifically in the image we're taking. And then the second row shows an overlay of the heat map on the original image with the same patch size of 2 and a jump size of 2. And then the sum of the square differences between row 1 and row 2 are shown as the delta. So how much does it actually change given the image? So as you see here in the second row, it's able to get this bottom middle part of the boat as the attribution part. But as we increase the regularization using both L1, L2, and elastic net, which is a combination of L1 and L2, it's able to show how much this is actually affecting the classification. Looking now at the robustness against adversarial attacks, we can examine the accuracy of both the training data and the validation data. As you can see, both with the base model with no regularization, with L1 regularization, L2 regularization, and elastic net regularization, all the time the accuracy increases both for the training data and the validation data. And as you can see the loss curve of the training data, it's similar loss between the base and all the regularization methods. But the thing to note here is looking at D, the loss curve of the validation data, the base model validation loss is beginning to show signs of overfitting as the loss starts to demonstrate high variance. So you can see that here with the blue line, and as you approach epoch 50 almost, it's going fluctuating quite a lot. So the loss is trying to overfit on that training data, and this is clearly evident here, where the regularization losses, L1, L2, and elastic net, are appearing not to overfit, which is good for generalization and increasing the sparsity within the model. So clearly here, the regularization is having an added benefit, not only to get like similar, if not better accuracy, but actually generalizing on the data and not overfitting. So if future data sets come in, they'll be able to interpret them better and hopefully get better accuracy. Here are some experiments and results that we have. So for the 3 different architectures that we tested on the ResNet, MobileNet, and VGG16, we did 4 types of experiments, both there's the base model with no regularization, one with L1 regularization, another with L2 regularization, and finally one with ElasticNet, which is both L1 and L2 regularization. And as you can see here, none of the models did better on their base model without any regularization. In ResNet, both fast gradient sign method and projected gradient descent did better on ElasticNet, and DeepFool did better with L1. MobileNet did better on L2 with both DeepFool and fast gradient sign, and better on L1 with projected gradient descent attacks. And finally, on VGG16, ElasticNet did the best against all 3 DeepFool, fast gradient sign method, and projected gradient descent. So this is able to show that the regularization actually benefited the models, and they improved better accuracy across all different attacks with using regularization. Overall, we were able to show that our models improved better with regularization, and that improving regularization increased the sparsity across the models, which is leaning more to biologically plausible neural networks, and that these principles are able to help in computer vision architectures for doing classification type tasks. Thank you. I hope you enjoyed the presentation, and now we're here if you have any questions, comments, or concerns.